Hello everyone, this is Arohi and welcome back to my channel Code with Arohi. In this video, I'll talk about YOLO version 4. So what is new in YOLO version 4? So if you'll see over here, we have bag of freebies, bag of specials, and then we are using this CSP Darknet 53 as a backbone, and as a neck we are using spatial pyramid pooling, and we have other modules also which we are using as a neck, and the head of YOLOv4 is having the work which is exactly same like YOLOv3, right? So these are the few things which have been introduced in YOLO version 4. Now I'll explain you each and every thing which is introduced in YOLO version 4, right? So now I'll explain you each and everything so that you can understand why these things get, why YOLOv4 is using all these things, right? So let's discuss each and everything one by one. Okay, so before moving to the functionality of YOLOv4 in general, how YOLO algorithm work. So what YOLO algorithm does is, suppose this is an image. So for object detection, what process YOLO follows? So it will divide this image into cells, and for each cell it will predict the probability of a class. If there is an object, then it will predict the probability of a class and will also tell us the bx, by, by, bh and bw. These are the coordinates of bounding box. So this is how YOLO algorithm work on any object detection task. Okay, and after that it perform non-mix suppression on it just to get the improved results, right? Basically this intersection over union is basically a loss function by which we are finally getting the correct results. Okay, so this is how YOLO algorithm works. Now let's start with the YOLO version 4. So this is the basic architecture of YOLO version 4. The first of all, the thing is input is going to backbone. Okay, this is basically, these are different blocks. So this block is called backbone block, and the task of this block is to extract features. Okay, so for extracting features in YOLO version 4, this CSP Darknet 53, we are using this particular network. Okay, so basically what is happening over here in backbone block, this block is responsible for extracting features, and for feature extraction we can use other CNN networks also. We can use VGGnet and we can use ResNet. Okay, but in the paper of YOLOv4 they have used CSP Darknet 53 algorithm for feature extraction. So once you get all the features extracted, so this is next block is neck block, and the task of this block is to collect the feature map from different stages. That's it. The task of this is to collect feature maps from different stages. All right, and then we have head. The task, see the guys, the task which we perform in YOLO version 3, the whole task we are performing over here. Head simply means we are performing object detection over here, we have a classifier over here, and we are bounding, we are plotting that bounding boxes also. So this is actually working as a YOLO version 3, right? So this is a YOLO version 3 which will detect the object and will plot the bounding boxes. This is just gathering the features together and giving to head, and this is for feature extraction. Okay, this is the main bounding block, this is the main architecture of YOLO version 4. all right, so as I've just told you, like we in the very first slide of our today's class, what's new in YOLO version 4, over there I have told you, like we have one concept with the name of bag of freebies. Now what is bag of freebies and why we are using it? See guys, obviously we every time what we want is we want to improve the accuracy of our model, and for improving the accuracy of your model. People or researchers are performing some new implementation, so that we can get more good results. So that is what we are doing over here. Bag of freebies simply means there are few techniques. Using those techniques we can improve the performance of our model. All right, now let's see what are those techniques. Using them we are improving our model performance. So this is data augmentation. So we already know, like before YOLO version v4 also, we are using data augmentation techniques to increase our data, so that on more data your algorithm will learn more, so obviously will improve the accuracy. So one of that concept, this data augmentation, you are already familiar with this topic. But yes, in YOLO version v4 there are few augmentation techniques which are new in YOLO version 4. Means before YOLO version 4 those data augmentation techniques were not used anywhere else. Okay, so we'll discuss that also. So how we are improving the performance of our algorithm? By performing data augmentation. I'll tell you one by one like what all data augmentation techniques we are using here in YOLO version 4, okay, in some time. And then we are using class imbalance, and the third thing is cost function. These three things comes under this bag of freebies, and we are using in YOLO version v4. So let's discuss it in more detail. So okay, so see, BOF simply means bag of freebies. For backbone means for this particular block. See, we have different bag of freebies and different bag of specials for backbone and for detector. Means obviously the task over here is different. We are extracting feature. So for improvement of the model we will be using some different kind of techniques. Okay, because the task of this block is different, so the techniques will be different. And over here the task of this head block, the task of this detector is different, so we are going to use different kind of bag of freebies over here. So these are the name of those bag of freebies which we are using over here, and these are the name of techniques which we are using under this detector category. Okay, so if I talk about this backbone, so the very first thing which we are using over here is cut mix. This is the data augmentation technique, right? And then we are using mosaic data augmentation, and after that we are using drop block and class label smoothing. So let's discuss one by one each of these features. So cut mix, first of all, just see these two, assume that these two images are training images. Okay, and cut mix simply means we will cut the random patches from our training images and will paste those patches on other training images just to create new samples. So that's what we are doing over here. If you'll see, these two are training images. From this particular training image I have cut this particular patch. Now in this particular patch what I'm doing is I have removed the patch from here, and in the same way I have another image. So what I'm doing is I have removed the patch from here and I have pasted that patch over here. What will happen by this particular way? We have increased the number of images, right? And our algorithm will get more view on different type of data, right? And now what is happening over here? You can call it cutout, because we have we have removed the patch from here, and the patch which we have removed from here, we have pasted that patch on another training image. So what is happening over here? Cut mix. Okay, so this is what cut mix is, and cutout simply means we have removed the patch from our image. So that now this is again one kind of example, and this is again one more kind of example. Now with this kind of example, what will happen with this kind of example? Let me explain you this with this example. So we have this image. Okay, So most of the time what will happen when we have these kind of image, most of the time our algorithm will focus more on the face, and on the basis of that particular face it will detect and tell us that this picture is of this object is a horse. But let's suppose if this face is hidden, right, behind the tree or something like that, if the face of horse is hidden, so what we want is, why we are performing this cutout, because we want to train our algorithm on these kind of scenarios also, so that because we want to improve the accuracy, right? So obviously in this particular case, if your algorithm is able to predict that this is a horse without its face, that means your algorithm is working fine, right? So that's why we are using cutout, because what we want is, if some of the portion of that particular object is not visible to our algorithm, then also we want that our algorithm should predict the results. Okay, so this is what cut mix and cutout is. Now let's talk about the next example, which is mosaic data augmentation. Now what this data augmentation is? See, this data augmentation simply means we are combining 4 training images into a one image with some certain ratio. Okay, so this is what, see, these are 4 training examples. Okay, now what we want is, we want to collect all these images and we want to make one image. So you can see, this is one example of mosaic data augmentation. What we are doing is, all the 4 images are here, these 4 training images are here. Now over here again we are combining these 4 images but with different ratio. So these 2 examples comes under mosaic data augmentation technique. Now what is the need of such kind of augmentation, right? So what happen is, let's suppose if your data if your image is on the scale is different, right? If the scale is more or scale is less, so with the help of this data augmentation technique, your algorithm will be able to work on such kind of problems also. Okay, so next bag of this freebies under this comes under drop block. Now what is drop block? See, drop block works as dropout. The way dropout works, the drop block works in the same way only. The only difference is dropout drops or removes the pixels which are in a continuous manner, right? Which are in, let's suppose 2 pixels are joining or 2 pixels are one after the other. So dropout works on such kind of pixels, and in drop block we are working randomly and we are dropping a block, right? So what will happen by using this drop block or dropout? Means this is just a regularization technique. We can improve, we can, this will help us in facing if you're facing the problem of overfitting, then you can use it over there, right? So this is what we are using in YOLO version 4 also. At which particular step we are using it? At backbone. Okay, the time where we are extracting the feature. Over there, what all bag of freebies we are using? We are using cut mix, and then mosaic data augmentation, drop block, and class label smoothing. Now what is class label smoothing? It's just basically what we do in class label smoothing is basically we are adding some noise in our class labels. Okay, so these are few techniques which comes under bag of freebies for backbone. Now let's see what we have next. Okay, now let's talk about bag of specials. Till now we have talked about bag of freebies. Now we are talking about bag of specials. Now in the same way, okay, let me show you with the help of this picture. Same again, bag of specials would be different for backbone because the functionality is different over here, and bag of special would be different here also. As per means, what we are doing is, obviously we will be using the techniques which are which will perform better for this particular detection layer, and we will use those techniques which will work better while extracting the features. Okay, so what all things we have over here? We have this mesh activation function. So there are lots of activation functions, right? Linear, sigmoid, ReLU, tanh. We have lots of activation functions, right? So here we are talking about mesh activation function, and over here we have cross stage partial connection, right? And then we have multi input weighted residual network connections. And if I talk about this bag of specials for detector, over here also we are using mesh activation. We are using mesh activation in both the scenarios. Okay, and then we are using SPP blocks and SAM block, and then pan path aggregation, and these things are there in bag of specials. Now let's start with the mesh activation function. So now what is mesh activation function? This activation function is performing very well with the problems with the object detection problem, right? So basically it has been proven that mesh activation function perform well as compared to ReLU and leaky ReLU, right? So that's why we are using mesh activation function in YOLOv4 instead of that ReLU and leaky ReLU. Okay, so if you see this picture, see, this is the output which you get after using ReLU activation function, and this is the output which we are getting after using mesh activation function. Now if you'll see both the images and compare them, what you'll see that in ReLU over here we are having very sharp and rough picture. This the profile is very rough over here, and the transition is very sharp in this particular picture, but over here we have very smooth transition, right? We have smooth profile and smooth transition over here. So you can see the difference between the output of ReLU activation function and mesh activation function. So mesh activation function will give you a better accuracy, and the picture, the output which you will get after mesh activation function, that will be more smoother. Okay, so now what is the see guys, I'm discussing more about mesh activation function over here so that you can implement this activation function in your examples. So that's why I'm giving you a proper formula, and then I'll tell you how to implement it in your with Keras, or how to write its code in Python also. I'll tell you that as well. So let's see the mesh activation function. So what we are doing is basically this activation function is a combination of tanh and then this soft plus, right, and then identity activation function. So it is a combination of 3 activation function, and the formula of this mesh activation function is this: x into tanh is the activation function, and then we are having a soft plus, this is again an activation function. So basically this mesh activation, this is the formula for it. And now let's see what is the formula for this soft plus x. So this is the formula for it, and then for tanh, this is the formula, and when you will combine both the thing, this is finally you will get, this is the formula for mesh activation function. Okay, so and this is how the graph looks like of activation function, mesh activation function. Okay, now let's see, let's suppose if you want to write this function in Python, then how to do it? See, the code is very simple. See, I have defined 3 functions. First function is tanh, and over here I have written the formula for tanh, and then next function I have created is soft plus, and this is the formula for soft plus, and then this is the mesh function over here. What I'm doing is I'm combining these 2 functions over here, right? So this is how you can write your own mesh activation function. Okay, and let's suppose if you want to use this mesh activation function with Keras, then how you can do it? This is the mesh activation function, the whole code which I've just explained you right over here, right? This is the activation. Now keras.backend.tanh, keras.backend.soft plus, over here you need to write x, right? And then you can call this mesh activation function like this. Okay, so this is how you can create your mesh activation function, and this is how you can use that mesh activation function in your Keras code. All right. Okay. So now what we have next? So now let's discuss cross stage partial connections. So what is it? It comes under bag of specials for backbone. Okay. So backbone simply means where we are extracting features. All right. So why we are using this cross stage partial connections? Okay. So basically, what will be the benefit of using CSP? See, using CSP, we can improve the learning capability of our CNN network. Okay. How? Let me show you. So guys, if you'll see this image over here, so these are the feature maps which we get from the base layer. Okay. So we are having, how many feature maps we are having? We are having 5 feature maps over here. Okay. And then what we are doing is, we are dividing the feature maps of the base layer into 2 parts. Half of the feature maps we have given, we have split it. Basically, we are performing splitting over here. Half of the features are here and half of the features are here. We are having 3 features over here and 2 feature maps over here. Okay. So, let's say x0 is the number of features which we are having at base layer, and x1 is this features and x2 is this feature. Okay. Now what we are doing is, check this picture now. So this is the base layer. At base layer we are having 5 feature maps. Now what we are doing is, we perform that split operation, and x1 means these 2 features. These 2 features are over here and they are directly going to at this stage, transition stage, and the features with x2 name, that comes under part 2, and these features are going through a dense block and then transition, and then we are adding concatenating these features and these features over here. So what is happening over here now? See, the very first thing is, duplicacy is removed. Duplicacy simply means duplicate gradient information. We are basically avoiding the duplicate gradient information. How we are avoiding? Because we are having these many feature maps and we have split those feature maps into 2 parts. Half of the feature maps are going through this area and half of the feature map are going through this area. So what we are doing over here is, we are removing the that duplicate gradient information. Okay. The second thing over here is, what do you think, what is the benefit of using this? So we are having 2 paths now for this gradient flow, right? So we are having 2 parts now. So one part is this, half of the feature maps are traveling from here and half of the feature maps are traveling from here. Now what will happen when we use back propagation, right, to update the weights? So at that particular time also we are using 2 paths now. What will happen when we are using 2 different paths and we are splitting the gradient information, and that gradient information is traveling from 2 different paths? What will happen? We will not face the problem of this vanishing gradients, right? Because we have split the data and then we are giving the data. So while updating the weights, while using back propagation for weight updations, we will not face the problem of vanishing gradients. And the next thing is, depth is also decreasing. Over here depth is this, over here we have divided those feature maps, and by that depth is decreasing, and computationally this will be good. Okay, if you'll see this concept computationally, if we have split the code in 2 parts, what will happen? Computation will be less, right? So all these things, this is the concept of CSP, and the task of CSP is only to divide the feature maps into 2 parts. One two parts. One part will go directly like this, and other part will go through a dense block. This dense block and transition, and then will get concatenated over here. And dense block simply means group of convolutional layers which are connected with each other, and each convolutional layer will have batch normalization and ReLU activation function, right? And the output of every previous layer will become the input to the next layer, right? Normally what happens? The output of previous layer will become the input of next layer. But in dense block, what will happen? The output of every previous layer will become the input of next layer. So this is what CSP is. Now the next topic is spatial pyramid pooling. Now why we need this spatial pyramid pooling? So see guys, why we need spatial pyramid pooling? First of all, let's start this discussion with why we use CNN, why we use convolutional neural networks. So we use convolutional neural networks for object detection or for object classification, right? And for basically CNN networks extract the features, and then we have fully connected layers which perform this object classification or object recognition, all right? And these fully connected layers accept the input of fixed size, right? And that's why we always need to resize our images, and then after resizing we give those images to our convolutional neural network and we extract features, and after extracting features we are giving those feature maps to our fully connected layers for the final results. Okay, so now the problem over here is that we always need to resize the images, right? This is the first problem. And the second problem is, if we are resizing the images, then the resolution will be affected, right? The resolution will get reduced. Resolution get reduced simply means we are compromising the quality of images, right? So these are the two problems with the normal convolutional neural networks, where we always need to resize our images. Resizing, first of all we need to resize, and if we are resizing our image, then this resolution thing is getting affected, all right? So the solution to this problem is spatial pyramid pooling. Using spatial pyramid pooling, we can provide any size of input image to our convolutional neural network, and the task of spatial pyramid pooling is to give us the fixed size dimension. Let me show you how it is performing this particular functionality. So let's see this picture. Let's consider this picture. So suppose this is a convolutional network and it is starting from here, and these are the fully connected layers which are finally performing object classification or object detection. Okay, so this is convolutional layer 1, data is traveling from this layer to this layer, and this is the last convolutional layer. Okay, and over here we are having 256 filters. Okay, and the size of filter map will always depend upon the input size of the image. So size we don't know, we have some random size, but the number of channels are 256. Okay, now after this is the block which is carrying code for spatial pyramid pooling. What this spatial pyramid pooling is doing? So over here the number of filters are 256 over here, and the size that will it is a random size, it will depend upon the input image. Okay, so over here you can see we have these three things. Okay, so what it is basically doing, this is a single bin, this is 4 bins, and this is 16 bins, right? So what we are doing over here is, over here we are covering our whole image in single bin, and over here we are covering our whole image in 4 bins. Basically what would be the output after this? See what we are doing over here is, the feature map is pooled to have 4 bins, and over here the feature map is pooled to have 16 bins. Okay, so the output which we will be getting after this is 16 into 256. 256 is the number of channels which we are getting from here, and over here the output of this is 4 into 256. This 4 means 4 bins, okay, and over here output would be 256 dimensions only, because we are covering our whole image in one bin only, right? And after that it is converting our image into a fixed size, and then we have fully connected layers, and fully connected layers are performing the output, okay. So this is what spatial pyramid pooling is, and just always remember why we are using spatial pyramid pooling, because what we want is we want to give any size of input to our network, right? And if we don't use this spatial pyramid pooling, then we always need to resize our images, okay. And I have already explained you what is the disadvantage of resizing your images. So if you want to give input to your network, and that input could be of any size of image, then you can use spatial pyramid pooling, because if you are using SPP in your network, what will happen? It will automatically improve the performance of your network, because over here we are not playing with the resolution, right? And we are giving more good quality data to our algorithm, okay. So this is what spatial pyramid pooling does. So guys, these are few basics of I have explained you the few things which are new in YOLO version v4. In my next video I'll explain you the code. Basically I'll show you a practical implementation of YOLO version v4, right, so that you can execute those, execute the whole code, and you can have your own YOLO object detector after that particular class. So thank you for watching.